Today we are going to do section 6.3, logarithms, which are very exciting, okay? Logarithms were originally invented to make multiplication easier. But nowadays we don't care about that because we have the calculator, but the logarithm still comes in very handy in a lot of ways. Now please turn to page 576 where we look at this graph right here. Where is the graph? This is the graph of y equal to 10 to the power x. As you notice, as the x-axis increases from 1, 2, and 3, the y-axis is going up fast, okay? It's 1,000. Why? Because y to the 10, if you plug in 3, x equal to 3, 10 to the power 3 is 1,000, right? So as you notice that the y-axis, you have to go all the way, compress it so that it goes all the way up to the 1,000 to be able to see this whole thing. Otherwise, it just took off and you can't. It's long gone, okay? If you don't, so this is not the proportional graph. This is when we compress this thing like by a ton so that we can see this far up. So that is the graph of the exponential function that we have already looked at. So what is logarithm? Logarithm is another way of saying the exponential function. For example, let's say 10 to the let's see log of well, let me write this down first. Now the logarithm log base of b of x equals to y. What does it mean? It means this, that in other words, this is another way of saying this. We are familiar with this because we just did it, right? And this is another way of saying it. So these two are equivalent statements. That is, if you have a base number, right, you raise it to the power y, that would be equal to x, and you can write it like this. So log bx means b to the power y equal to x. In general, b to this thing, okay, when you write down log, the base raised to power this one equals to that is what log means. Now that sounds a bit confusing. So let's look at some examples of what we just looked at, right? We have 10 to the power x. Let's say y equal, let's say b equal to 10 in our case, as an example. So if b equal to 10, then let's figure out some numbers. What is log b 1 equal to? What does that mean? Being that b equal to 10, that's 10 to the power 1, okay? And x is the base times, wait a second, let me think about how I want to say this. Okay, let's start with 10, okay? That is easier. So in other words, what the question is, b to the what power equals to 10? Well, where b is 10 itself, okay? This equals to what? Now if base is 10, that means 10 to the what power equal to 10? Well, that would be 1. So then log b of 10 equals to 1 if b itself equal to 10. Now let's think about another example, okay? Let's say log b is still 10, okay, of 100. What does that equal to? That means 10 is the base, 10 equal to what power equal to 100? And that would be 2. So the answer is 2, okay? And let's continue. Now the next question, log base to what power? B of 1,000, let's say. What would that equal to? Well, then you ask yourself, b to what power? B is 10, okay? So 10 to what power equal to 1,000? And the answer would be 3, okay? 10 to the third power, 10 times 10 times 10 is 1,000. So this answer is 3. So as you can see, that's how the log is just another way of saying this. But it's a little bit turned inside out, so it takes a little bit getting used to. So the way you get used to it is just do a whole bunch of this stuff until your brain gets comfortable with it or sick of it. Either way, okay, same thing. So then next, let's consider log base. Let's consider the next question. Log b is still 10, okay? B of, let's say, I wanted to figure out log b1 equal to. That means b to the what power, or 10 to the what power, equals to 1. Well, 10 to what power equals to 1? There's only one power that everything to that power equals to 1, and that would be 0. Okay, so log b of 1 equals to 0. In fact, that's true for any number for b. Okay, not just 10. I think log of various things, okay, as long as positive, is always equal to 0. Now, remember the log bases are always positive because, as we mentioned before, this number b for exponential functions, we require it to be positive, okay, bigger than 0, and because negative numbers give us a big headache, so we'll ignore them. So the b is always positive in logarithm. So b and any b, this is always true. Okay, but anyway, so this is what we're talking about today, this entire situation. And anytime you see a problem, when you read this thing, you will ask yourself, you will say b to this power has to equal to that, or put it, which is another way of saying this. See, b to the y power equal to x. The same thing here, b to the y power equal to x. And that's what we're going to build our entire section on, this equation, this equivalence alone. It's not really much of an equation, it's more of a equivalency. Okay, that is, we're saying this in a different notation. And that's the only thing you have to get used to, is this different notation of saying this. All right, so having said that, let's look at an example. Right? Example 1. Okay, this is on page 577. So let's look at problem example 1 on page 577. The first example is when you're supposed to calculate this thing. What is that? That equals to, okay, what this means is, let's say this equals to what we're looking for. Okay, it equals to x. That means by this statement that what's on the base to this power equals to what's inside. Okay, in other words, 6 to x power had better equal to square root of 6. See, always remember the base times this thing, what it equals to, has to equal to what you're taking the log of. That's what log means. So 6 to the power x equals square root of 6. Well, that means just by looking at it, 6 to what power is square root of 6? Square root of 6 is also 6 to 1/2 power, right? So then x has to be 1/2, and that's the answer. Similarly, this is 3 base to what power? Let's say this equal to x. 3 to x power had better equal to 9, okay? You see, base to the power equal to that, all right? And therefore, as it says here, see, x base to the answer, base to the answer equal to what you're taking the log of. So 3 to the power x has to equal to 9. Well, then x then has to be 2. Okay, 3 squared equals 9. So that is how we do example 1. Okay, so next, turn to the next page. Let's look at example 2. All right, for example 2, we have there are 3 things, right? And we need to write this. This is similar to that, and we just have to convert this into the logarithmic form. So then this is this thing is always the base. Okay, so for this is part A, we'll write down log 2. Okay, and this is log 5. Whatever the base is, base 2. The b has to be written on the bottom. There. Base 2, that's log 5, and that's and the last one is log 10. Okay, that's the base. I'm just writing them all at the same time. And so that's b, okay, which is this one. And then y is the answer, but x is what it equals to. This is log base of 8. Okay, and this is so what it's equal to. So this is log 525, and this is log 10 of whatever it equals, right? Yeah, of 1 over 10,000, 10,000, blah blah blah. Okay, so that is the logarithm. So that's we're rewriting this equation to exactly like this. Okay, exactly like this form. So make sure that I got it right. Okay, this number is the base, so that's the base, and whatever's on top is what it equals to. So, but what's x is what the solution is. Okay, so that's 8, 25, 10,000, 1 over 10,000. So what does that equal to? This one, and the result is actually the result of the log is the exponent, you notice, okay? So let that equals to 3 because that's the exponent. This equal to 2, that's the exponent. And this equal to -4 because that's the exponent, okay? So I want to show you that I'm just following this formula here, okay? Kind of like a recipe, exactly. And that is, that's how you rewrite each exponent form in log form. Again, these are equivalent statements. This says this, okay? Just like these two are equivalent. So that's example 2. Yeah, and so next let's look at example 3. And okay, so example 3 on the following page. Now example 3 on page 579 says the problem is y equal to log 4, 64. Now how would we calculate that? Well, we just translate the log into this equation, okay? Now it says b, that means what's x in this thing? X is, well, log, yeah, x in this equation will be 64. Okay, that means 64 equal to b, which is this number down here, okay, equal to 4 in our case, that's b, and then to some power, and the power will be y, okay, we'll call it y. And what we're looking for is what is the value of y, because y is the value of the logarithm. Okay, so in other words, 4 times what power is 64? And if you think about that for a few seconds, then you realize that is 3. Okay, y would be equal to 3 because 6 to the 3rd power is 64. 4 times 4 is 16. 16 times 4 is 64. So 3 fourths multiplied together would be 64. And therefore, y equal to 3 is the solution to this logarithmic problem. So as you can see, we continue to do this, and this might seem like, why are we doing this? Why don't we just stick with that? We already got that. The reason is that this format does become very useful. It takes a little adjusting, getting used to at first, but once you get used to it, the function gets very handy. Okay, so it's worth it for you to do a bunch of this stuff until you know this like the back of your hand, and then it just becomes very comfortable. And but you always remember that what this means is that when you calculate log bx, what that means is asking yourself b to what power equal to x, and that's the value of logarithm. Okay, so b to what power equal to x. Okay, so let me erase the board. Next, let's do example 4, again on page 579. Please do all these examples yourself too. As you notice, they're very fast, okay? Especially once you get used to it, they're even faster. You can really crank these things out by the boatloads. Anyway, so what's example 4? We need to calculate y equal to log 3, 1 over 27. All right, so to calculate that, we need to rewrite this thing, okay, as some kind of exponent because it's related to it. So we'll rewrite it as log 3. Okay, what's 1 over 27? That's 3 to the power negative something, and minus 3, right? 3 times 3 times 3 is 27. And when it's 1 over, it's always a negative exponent. Please review chapter 1 where we talk about this type of thing if you have become rusty about this type of stuff. So anyway, so what is that? Well, the logarithm basically wants you to plug out what is the exponent, okay? What's y? Well, in other words, we want to know what is 3 times what power, okay? 3 times, in other words, see, b to the power y equal to x, okay? Where logarithm equals to y. So we write down equal to y. And then, so which means 3 to the power y following, b is 3, right? 3 to the power y has to equal to x. X is this stuff. in here, okay, equal to x, which is 3 to the power minus 3, which means y equal to minus 3. And that's our answer right here, because that's y. Okay, so that is the answer here. Generally speaking, you're just asking, you're plugging the power out of, basically, of this thing to calculate the answer. Let's look at the next thing. There is something called a common logarithm. And the common logarithm is used in the past anyway for helping you do multiplications and also divisions. But we don't care about that now. So it's not. So the common logarithm isn't used as much now as in the past because, as a result, but we still call it the common logarithm. And let's see, even though hardly anybody uses it anymore. So the common logarithm just means we choose the base to be 10 because we like our numbers to be base 10, okay? And so let's choose 10. And then, okay, so having said that, let's turn to the next page and look at example 5. Now, so here's the word, we're calculating in example 5 log of 1,000. Now, as I mentioned, this, if you don't have a number written down, it means base 10. Well, it used to anyway. This is back in the days, like when I was in school, back in the days when they have no calculator, what you do with multiplication of complicated numbers is that you look up log base 10 of that number, say 1,556 or whatever. If you have, say, 1,556 multiplied by some other big number like 2,653, let's say, if instead of multiplying by the numbers directly, which will take you forever, what you do is you look up each number in the logarithmic chart, okay? And then what happens, then you can add it up. And so your multiplication got changed into addition. The result you get is an approximation, but it's a very close approximation. You look it up on these tables, which was just the worst thing that can happen to anybody. Now, so I had to use those charts, but at the time when I was in school, you might think, wow, that is that like such a long time ago? Well, are you that old? I'm not that old. See, I'm old, but even I'm not that old. What happened is the school I went to decided that it was good for you to learn how to use the old-fashioned tables. They were the worst. I was always reading the wrong row or column or something. It was, it was horrible. Even though we had scientific calculators at the time, and it wasn't expensive either, everybody had one, but we were forced to learn from the tables first to, I don't know why, okay? It was the worst thing ever happened to me. But anyway, so nowadays you don't have to do that, but I just want to explain why this thing is called the common log. It's not, okay? Nobody does that anymore. So nobody uses base 10 that I know of. With that anyway, so nowadays we have, we still stick with, for now, in algebra, the tradition that if you don't see the number here, it means base 10. So in other words, we need to now calculate what is log of 1,000. In other words, we need to figure this equal to y. And following this formula, that means the base, which is 10, if it doesn't say, it means 10. Okay, 10 to the what power, y, has to be equal to 1,000. Oops, okay. Equal to 1,000, and that means y had, come on, okay, 10 to what power? 10 multiplied by itself, how many times will be 1,000? The answer will be 3, okay, 10, because 10 times 10 times 10 equal to 1,000. So you notice the logarithm doesn't give you very big numbers, okay? Because we're taking the log of 1,000 and it only got to 3. And in general, as you can see, log of 10,000 is only 4. Log of 100,000 is only 5. So the logarithm grows rather slowly, okay? And so that is in fact one reason we use it. It's because of its incredibly slow growth. Okay, so that's example 5. Next, let's look at example 6. No, let's skip example 6. It wants you to calculate log, well, do it yourself, I guess. It's easy enough. To calculate log of something on your calculator, you just punch it in, okay? There is a log, and we'll talk about that later. So yeah, do this yourself, I guess. And you just punch log, and then punch in the number that you need to calculate the log thereof. And yeah, and I don't even think you need to do parentheses. But we'll do that at some point. Should we do that now? Fine, let's do it now. All right, so I punched in log 3 to 1. The first parentheses was already in there for you, okay? So I suppose we'll type in the close parentheses to be complete. And then, yeah, and then call it done. It comes up to some number. All right, I just pushed in log and the log showed up. And it gives us some number, and that should be correct. It's 2.5 or something. Yeah, it's 2.5. So yeah, so please, excuse me, please do that yourself. And then we'll go to the next page. What are we doing? Again, it's a similar story, okay? 10 to the power x equal to 500. So, all right, let me write that down. Okay, now this is problem, I forgot to write down, this is example 7, all right? I'll write down example 7. So 10 to the x power is 500. Now we'll follow this plan right here, okay? What's the base? Base is whatever, this thing is the base. So we have log base 10, okay? Which we don't have to write it down, but according to base 10 of 500, base 10 of the value here that is given, that is y, okay? And that is equal, 500 is our y, x equal to b to the power y. No, that's x. Let's see, well, yeah, that's right. So this is b and this is x, right? Okay, I follow the formula, and then this value will give us y, right? Yeah, it says right here. See, y equals to log base, and then the value of x being the this value. Wait a second, did I get it confused? Well, for this problem, they reverse the role of x and y, so we're not going to call it that, okay? The point is that 10 to what power equal to 500, which is the same as saying the base equal to what power equal to 500, okay? That is what we're looking for. So make sure this thing checks out, and that's about it, okay? And to calculate that, we just type it into the calculator. All right, and I should say that this is x, because the reason is because this problem calls the exponent x, okay, instead of y. So that the rows got reversed, but the idea is the same. There is no difference. So x equals to this stuff. As a result, we just have to calculate log 500. On the calculator, I should mention that the word log means base 10. Okay, it still follows the old tradition, where if you just see log, it means base 10. And then we'll push the equal sign. I just type, and that equals 2.6 or 7 or whatever. Yeah, it's about 2.69. What does it say? Yeah, it's good enough. So that is the answer to example 7. Please do that yourself as well. Bear in mind that in this problem, the x and y rows got reversed, but otherwise there's no difference, okay? Still, yeah, that means that. Well, anyway, so let's keep going. The next concept we are going to consider on the same page, 581, is a natural log. The natural log is using the base e. The e is that number that we mentioned some time ago. Okay, e equals 2.718, and that is not critical for you right now. Then the point is for the base e, it comes in handy, and of course it has a name to it, and it's the natural log, which we have mentioned. I think we have even mentioned it before. No, we haven't. It doesn't matter. See, the natural log is ln, and that is how we're going to punch it into the calculator. Nowadays, the natural log is used far more than base 10. I don't think, yeah, I doubt anybody even use base 10 besides earthquake scale or something like that. And even earthquake scales might even be changed. I don't know. But we're going to talk about earthquakes before the end of this this section. So anyway, the log, natural log, is defined as log base e, where e is equal to 2.718, etc. Okay, 2.718. You don't have to worry about why we need a natural log right now. It's just something that end up being very useful in various mathematical calculations. So that's called the natural log, and let's look at the next example. Okay, let's calculate the natural log of something. Please look at example 8 and punch it into your calculator right now. All right, so that's what I did. Okay, and natural log of 500, you just punched it in. The natural log is that button right there on my calculator. Anyway, if you punch it in, yeah, and then I will give you some number. Okay, we don't really care what that means right now. It means e to that power equal to, what is that, 6.2? What is this, 500, okay? And so that equals to 6.2, and as always, that means the base, e to the 6.2 power, e to the 6.2 power, or whatever, yeah? It will be equal to 500. If you punch, is what that means. That is, the base to the power you found is going to be equal to that number, is what this logarithm means, okay? As always, this thing, in other words. All right, so that's good enough. And I guess that is the end of this section. All right, so now before we come to the very end, I have before I start assigning homework, I want to talk about something, if I can find it. Earthquakes, there it is. I want to talk about earthquakes, okay? Nobody is going to talk about logarithm without talking about earthquakes. Now, earthquakes are measured on a scale that's base 10. Now, what that means is the unit of earthquake is you're measuring only giving you the exponent, okay, of how powerful the earthquake is. The reason is because the earthquake power increases logarithmically, and I should say exponentially, and that's why we use the Richter scale, and I want to show you what it is. Okay, here's something I got from the internet. Now please look at this. Okay, here's the earthquake scale. Now the magnitude of an earthquake, if it's like about 3 or so, okay, 3 or so, then you can feel it, but it doesn't cause much, if any, damage. Okay, maybe the ground shakes a little, but no harm done, kind of a thing. So at 3, it's the earthquake scale is done by base 10, I believe. Now, so therefore, the 3 means 1,000. In other words, 3 means 10 to the power 3. Okay, so 3 means 1,000, and we'll call it here 1K. And we'll use K as the new unit. That is, 1,000 is roughly when humans can sense it, right? And then, but it's not horrible. So in other words, this we'll call it 1 unit of earthquake strength in terms of measuring earthquakes. Now, next earthquake. Let's look at this one. A lot of damage is earthquake scale of about 6 right here. What is 6? 6 means 10 to the power 6. And remember, 10 to the power 3 is 1,000, right? So 10 to the power 6 is 1,000,000, okay? That is 1,000K. In other words, by the time it causes a lot of damage, it's 1,000 times stronger than the one that you can feel it, but it doesn't hurt anything. By the time it's 1,000 times stronger, then it's gonna cause a lot of damage, especially where there are a lot of people. Next, let's consider, here's the San Francisco earthquake, which is supposedly 8.0. And I want you to calculate how many times that is compared to the earthquake you can barely feel, you can sort of feel. And so now I did the problem, well, you can do this basically in your head because it's 8.0, okay, compared to, say, 3. Now, I did the problem that is this one. This one is the biggest earthquake in the United States. Now, that is happened as a 10 to the power 9.2, and that means 1.6 million K. That is 1.6 million times stronger than the earthquake that you can feel. So you can just about imagine how much stronger that is. And that also explains why the earthquake scale is done this way, because by 9.2 it is a million times stronger. So instead of saying, talking about numbers in the millions, we simply give it a number of how many zeros, basically is what that's saying, right? And how many zeros we're talking about. So that is why earthquake scales are done with much smaller numbers, so we don't have to quote how many millions. So 9.2, as you can see, is a million and more than 1.5 million times stronger than the earthquake that we can somewhat feel. So that is, of course, going to cause incredible damage. So that is So please do the San Francisco one to see how much stronger it is this as part of your homework, okay? And yeah, and that should be 100. I don't know. Yeah, I think 100,000 times stronger is probably the answer. But yeah, please calculate that yourself. So for homework, on page 571, please do problems 7, 11, 15, 19, 23, 25, 27, 31, 35, 37, 39, 41, 43, 45, 47, 49, 51, 53, 55, 57, 61, and 63. Now that sounds like a lot of problems, but as you can see in the examples, most of the problems you can do it quickly, and you can do it even quicker once you get used to this. Okay, what are we? This thing right here. Once you digest this thing, you can crank out the homework rather fast. Most of them, anyway. All right, so please go do your homework, and when you come back, I want to talk about some of them. All right, now let's talk about some homework problems on page 583. The first one I want to talk about problem 35, natural log of x equal to 2. What that means is whatever is base, okay, remember base raised to this power equal to that. So base is e, okay, anytime you see natural log, the base is e, which is 2.718, but we don't care about what it is right now. It's like pi. So e raised to this power is going to be equal to x. That's following this definition, okay? Base times what it equals to is going to be equal to that thing. So e, okay, raised to the power 2 equal to x. Now, having said that, that's the answer. Piece of cake, right? So next, let's look at the next problem. All right, the next problem, we have this thing plus 4, but let's figure out what this is for first, okay? Then we'll add 4 to it. So let's say this thing, how would you do that? Let's say this thing equal to x, and then we'll do something. What does that mean? We'll change it into the logarithmic form. That means a natural log. Being that we're dealing with e here, we'll use the natural log. Natural log of x is going to be equal to, natural log of x is going to be e to the power, natural log of x is going to be equal to what's on top, right? See the log base of x is equal to the exponent. So that is this exponent right here. Natural log of 10.125 or whatever it is. So if the natural log of x is equal to the natural log of 10.125, in other words, x is 10.125. Okay, so that is x is exactly this thing, because we have it lined up, right? 10.125, and that's the answer. So that's what this thing is. So x is exactly, in other words, when you have e to the natural log, it is exactly the value that's in here. And this is the argument why that is the case. Now, if x is 10.125, and then you have to add 4 to it to get the right answer, that'd be 14.125. And as I check the answer at the back of the book, I'm right. So that is that. By the way, this is problem 41. I only wrote down 4 there for some reason, okay? But it's problem 41, and x is just exactly this thing. Next, let's look at problem 45. Now, we have 6 log 8, 4. Well, we'll ignore the 6 for now, okay? And just figure out what log 8, 4 is. Now, by this definition, that means 8 to, if we call this y, let's say, like, okay, just the log part, okay? We'll ignore the 6 for the moment. So just this part, if this part equals to y, that means that the base, which is 8, following this equation here, 8 x equal to x is in here, okay? The 4 equals to x 8 to the power y, right? So in other words, we need to figure out what y is. We need to ask ourselves question, give me a second here. All right, so let's do that. So to do that, we have, well, there's no direct answer, 8 to what power is over 4, so we'll do some tricks from chapter 1, okay, concerning exponents. So 4 is 2 to the power 2, and 8 is 2 to the power 3, right? 2 to the power 3 times y, the y is still there. In other words, 3y equals to 2. If we identify the exponents, which means y equals to 2 over 3. And then, and that is the value of y that we're looking for. So this part is 2 over 3, okay? And did I say 2 over 3? Yeah. So then the whole thing would be 6 times 2 over 3. 6 times 2 over 3, cancel out the 3, that should be equal to 4, and that should be the answer to this problem 45. That's correct, okay? I just checked the answer at the back of the book, and it is right. So that's that. Next. So problem 49, we have that, which we'll call it similar to this. We'll call it this equal to y. Again, I'm only referring to the log part, okay? We'll deal with the 2 later. So let's figure out if y equals the log 100 to the minus 3, what is y? If it's just this log, it means base 10. So from the definition here, we get, so the base 10, okay, to the power y, which is what we're looking for, has to be equal to what's in here, okay? What's taking the log of, which is 100 to the power negative 3. And now we have to solve this exponent equation. So what we do is write this thing, that 100 is 10 to the power 2, okay, times minus 3. And then, so then we identify y equals to 2 times negative 3, which is minus 6. And then the whole answer then, so this part is, yeah, just this part is y is minus 6 times 2, so the whole value, the answer will be minus 12, which for problem 49, yep, that is correct. So the total answer is 2 times negative 6, and that's that. Okay, now problem 53, we need to calculate 25 natural log e to the 2/5 power. Okay, again, we're going to do this trick where natural log means the base is e, and e is a number, 2.7, whatever, we don't care what it is right now. So we need to follow this equation. So let's say this equal to y as the formula states. Okay, just this part. We'll worry about the 25 later. So this, let's say if just this part equal to y, then that means by this definition, that means the base, which is e, okay, e to the power y is equal to what's inside the x. What's inside is e to the power 2/5. That whole thing is inside the logarithm, e to the power 2/5, and that means e to the y is e to the power 2/5. That means y is exactly 2/5. So y equals to 2/5. And but we need 25 times y, okay? So 25 times y would be cancel out the 5, and you got 5 times 2 is 10. So problem answer for 53 should be 10, and it is. So next, let's look at problem 57, log square root of 2. We just have to punch it into the calculator. So let's do that, okay? So I have push in log. Oops, I need to turn my calculator on first. Log square root 2. Okay, I punched in 3 buttons. Log square root 2. We'll push in close parentheses. No, wrong. Let me push the delete button, which I need to find. There. Okay, log square root of 2. And then I need to get out of there. Okay, get out and then push the close parentheses. See, that's better. You don't have to probably, but to be complete or reasonable, let's type it in. So push equal signs, 0.15, that should be the answer. That's problem 57. Yep, that is correct. So next, let's consider problem 63. First, let's pay attention to the denominator, okay, where it says natural log of 1. And let's figure out what that is. The natural log of 1, as they've defined, it means equal to y, let's say, okay. Again, that's calculated by this rule here. That means e to the y power, okay, e to the y power has to equal to 1. By this definition right here. Now, what e to what power equal to 1? There's only one power that everything to that power equals to 1, not just e, and that would be 0. Okay, everything's 0 power equal to 1, and so natural log of 1 equals to 0. And being that you cannot, this and that thing is in the denominator, we cannot have zeros in the denominator because it is impossible to divide by 0. And therefore, there is no answer to this question. Oh, actually, it says, is this true? Of course not. It's not true. Okay, so that is, that's that. And that marks the end of this section.